Okay, today we're going to be talking about strong acid and strong base titration curves. Right here we can see that we have a strong acid right here, and it was titrated against a strong base. So it starts off quite low, and then as we add more and more base, so on the bottom right here, this is the amount of base added, so this is base added. And as base is being added, it stays relatively flat for most of the time, and then as we get very close to the equivalence point, it starts to rise up very quickly, and then until it reaches the equivalence point right here. So at this point right here is the equivalence point. Now, the equivalence point, the amount of volume at the equivalence point, we can just go VB, which is the volume of the base. Now, whenever you titrate a strong acid and a strong base together, the pH is always going to be 7. The reason why is because the salt that is made at the end of the titration is a neutral salt. So let's take, for example, a strong acid and strong base titration. So here we'll write an example. So we have a strong acid like HCl, and we titrate it against a strong base like NaOH. And we see when this reaction occurs, if we reach a equivalence point, a stoichiometric equivalence point, or in other words 1 mole of this and 1 mole of this, what we'll get is NaCl and water. Now, water is, as we know, is a neutral substance, and NaCl, well, Na is a spectator ion and chlorine is also a spectator ion. Since these are both spectator ions, this is a neutral salt. And therefore, our pH is going to be 7. Okay, so we see here at the equivalence point, pH is 7. Now, what we're going to look at now is what happens if we have a strong base, but instead of a strong acid, we have a weak acid. So that's the next one we're going to look at. So here we have a weak acid and a strong base, and there's a few differences to the titration curve. The first major difference is that the pH is greater than 7. So here's the pH down here. As we see, it's quite low. Here's 7, and it's quite low, and the equivalence point is much higher. And the equivalence point has a pH of maybe 7, 8, 9, 9 and 9.25, 9 and a third, 9.3 about a pH. So the pH is much higher. That's the first major difference. And the second major difference is that we have this weird little anomaly right here, this kind of sudden rise in everything. So this is a point of interest, and this is because it's a weak acid. Now, as we know from weak acids, that whenever you have a weak acid, not very much of it ionizes, not very much of it becomes acid. So let's take an example right here of saying my favorite acid, hydrofluoric acid. And at the very beginning, when you have hydrofluoric acid in water, forms an equilibrium with water and forms H3O plus and F minus. So that's the initial pH right here before we add any base. Now, when we add some base, the base combines with the H3O plus and forces more HF to ionize. Since it forces more HF to ionize, the concentration of fluorine increases. if we have an increase in the concentration of fluorine, it kind of wants to prevent some of this from ionizing. And then the OH kind of builds up, and the H3O plus decreases even more. And therefore, since the H3O plus decreases even more, we get a really sharp rise at the very beginning. What's essentially happening is what we call the common ion effect. If you remember from chapter 3, we have a high amount of fluorine and a relatively low amount of H3O plus, and since we have a high amount of fluorine, it's kind of forming its own equilibrium. These won't be equal, and therefore the amount of OH can build up a little bit faster, and we get a very sharp increase right here. So these are the two biggest differences. One, a pH that's really high, much higher above 7, and we see this kind of weird thing. Normally what would happen if it was a strong acid, this line would go something like this. It would become off more straight. But since it's a weak acid, we get this line down here. Okay, so those are the two biggest differences between weak acid and strong base, and strong acid, strong base. Now let's look at what we can do with a titration curve and how we can calculate this kind of stuff. So the first thing we want to talk about is how to calculate Ka for an unknown weak acid. So at the halfway point to the equivalence point, the conjugate acid is equal to the conjugate base. Half of the weak acid is changed into its conjugate base. So here's some notes for you to kind of think about, but I'm going to do an example that proves this, and we're going to derive a small formula that can help us calculate Ka. So imagine we have 1 mole of some unknown acid. So we start off with 1.0 molar acid, and as it says here, at the halfway to the equivalence point, we'll get something. So remember, equivalence point would be 1 molar of this plus 1 molar of OH. That would be equivalence point. So half of the equivalence point would be 1 molar of the weak acid and 0.5 molar of the base. Now these two have yet to react, so this is 0 and H2O is a liquid, so we don't really care about it. But if these two are going to react, it is quite clear that HX is in excess, and since everything is on the reactant side, the reaction is going to go forward, and HX is going to decrease by 0.5 molar because it's going to react with all of this. Now since all of this reacts, it's also going to decrease by 0.5 molar, and therefore X minus is going to increase by 0.5 molar. So if this was our ice table, what we see is HX is going to be 0.5 molar. This one is going to be approximately 0 molar, and X minus is going to also be 0.5 molar. So if I were to write my Ka expression for this, it would be Ka is equal to X minus times by now my times by my H3O plus divided by HX. Now you might be wondering, where did I get this H3O plus from? So remember, Ka doesn't involve the OH here. So this is the acid and this is the base. This is the weak acid right here, and this is the strong base right here. So how did I derive this formula right here? Well, I derived it from just looking at half the equation. I'm just looking at the HX plus water forming an equilibrium and making X minus plus H3O plus. Now, since we're not changing the temperature, the Ka is going to be the same, even though we're adding the OH. So this is still going to have a concentration, equilibrium concentration that's 0.5, and this is also going to have a concentration of 0.5. Now, if this is 0.5, and this is 0.5, now that leaves just this. So imagine, again, this is 0.5, and this is 0.5, okay, from this equation right here. Now, plugging these numbers into our Ka, what we find is that our Ka equals just our concentration of H3O plus at the halfway point. Okay, so that's where it equals at the halfway point. So in other words, since Hx and x are equal, this cancels with this, and you're left with Ka equals H3O plus. Okay, so if we're to look at that on a graph, this is kind of what we would see. So I'm going to erase this all really quickly, and then we're going to look at another one. So here's the graph that we were dealing with earlier, and we see that the pH half is right about, I don't know, maybe right about there is pH half, which is about 12.5 milliliters. Now this is 25 milliliters. This is the equivalence point. So the volume, the half of it, would be 12.5 milliliters. Now if we were to draw a perfectly straight line, which I'm going to attempt, right up to there, and then another perfectly straight line right to there, we see that it pretty much lands directly on pH 5. Okay, so in order to calculate the Ka, we can use the pH halfway, and we know that the pH halfway is equal to 5.0 based on the graph, and we also know that Ka equals the concentration of H3O plus halfway. So I'm just going to use this as a subscript to indicate halfway. Now therefore Ka equals 10 to the minus 5.0. Okay, so our formula for calculating changing pH into H3O plus, and therefore Ka equals 1.0 times 10 to the minus 5. Okay, so yeah. Now, when we talk about the halfway point, there's a big distinction between the halfway point. Now, it does not mean halfway on the y-axis. It means halfway on the x-axis. So again, if 25 milliliters is the VB, or in other words, 25 milliliters is the volume of the base added, 12.5 milliliters is the volume of the base added halfway. Okay, now we can see here that the pH is about 5 here, and it's 7, 8, 9, 9 and 9.3 right here. So it does not mean half of the pH, it means half of the volume. And then we just simply read the pH at half the volume. Okay, so there's a bit of a distinction right there. Now, and that's how you calculate Ka using this graph. Now, how can we calculate the initial concentration of the weak acid? So right here is the initial pH of the weak acid, but I want to know, or we want to know, is what is the initial concentration of that. So what we call right here, this point right here, is our pH initial, our initial pH, our pH before any OH is added. So let's take a quick look on how we can calculate that. So what we can do is, if we take a formula, so we're not adding OH, this is before OH is added. So what is happening is HX plus H2O, and again that makes H3O plus X minus. So before any base is added, we want to find out what is the concentration of this. So I'm going to make a quick little ice table, and we want to know what is the concentration of HX. Okay, before it ionizes and becomes H3O plus. So before it ionizes and becomes H3O plus, the concentration of H3O plus is 0, and X minus is also 0. And this is going to, since it's 0 and this has a number, it's going to, the equilibrium is going to shift right, and therefore this is going to decrease by a factor of X, and this is going to increase by a factor of X, and since it's 1-to-1 ratio, it's going to also increase by a factor of X. So the constant H3O plus is going to be X, this is going to be X, and this is going to be just HX minus X. So if you know the Ka, you can calculate the initial concentration of this by going, well, products over reactants, which will be X squared over the concentration of HX minus X. Okay, so HX meaning our unknown acid, and you can calculate this by rearranging this formula and solving for HX. Now let's take a little bit more of a practical aspect and try to figure out what is HX using this graph right here. So I'm going to erase this right now that we have derived the formula for how to solve it. So what we see here is we know that our Ka from our last problem is our last slide, our Ka is equal to 1.0 times 10 to the minus 5, and what we can clearly, well, a little bit here is that our pH initial, so our pH initial is around 2.5, so 1, 2, about, yeah, 2.5 or so. 2.5 is equal to our pH initial. So if we were to take our pH initial and calculate our H3O plus, So therefore our concentration of H3O plus initial is going to equal, well, 10 to the minus 2.5, and therefore our concentration of H3O plus initial is going to equal 3.16 times 10 to the minus 3 molarity. Okay, so we know our Ka and we know our H3O plus initial. So again, this is before we add OH, so we're going to write a new formula here, and it's going to be HX plus H2O, and that forms a equilibrium and makes H3O plus and X minus. Now, again, our ice table. So our initial concentration of HX we do not know, but I'm just going to write HX. Now our initial H3O plus, well, is 0, and X minus is 0. Now this is going to shift right, and we know that the final concentration at equilibrium, based on the graph, is 3.16 times 10 to the minus 3. So the concentration of H3O plus is 3.16 times 10 to the minus 3, and therefore, since it's 1 to 1 to 1 ratio, this is also going to be 3.16 times 10 to the minus 3. That means this had to increase by 3.16 times 10 to the minus 3, and this also had to increase by 3.16 times 10 to the minus 3. Now, therefore, since it had to shift right, this had to decrease by a factor, by an amount of 3.16 times 10 to the minus 3, and at equilibrium, our concentration of HX is equal to HX minus 3.16 times 10 to the minus 3. So if we were to put this in our Ka expression, which is going to be Ka, which is equal to H3O plus times X minus divided by our HX and then at equilibrium. So in other words, this number right here. Okay, and what we can see is that if we were to plug in all of our numbers, our Ka, which we know is 1.0 times 10 to the minus 5, so we're just going to plug that number right in. 1.0 times 10 to the minus 5 is equal to 3.16 times 10 to the minus 3. Okay, we're getting these numbers from here, and this is, since there's two of them and they're equal, we square it, and this is going to be divided by our concentration of Hx minus 3.16 times 10 to the minus 3. So what we can say is, what we can do is we can just solve for Hx. Okay, and if you solve for Hx, you'll find, so you multiply 1 times Hx minus 3, and then you solve everything for here, you'll find that Hx equals 1.0. Okay, so now we have calculated the initial concentration of the weak acid before it ionized. Okay, so after it ionizes, it would just be 1.0 minus 3.16 times 10 to the minus 3, which is actually kind of an insignificant number in comparison to right here. Now, what we're going to now we're going to try some other questions right now. Okay, so here's a practice question that I want you to work on. Now, it's a question that instead of giving you a graph, it just gives you a few different numbers. So it says that you are given a monoprotic weak acid, which is quite important to know. So you already know a little bit about what the graph looks like, and you're told that you're given 25 milliliters of this. Now, to reach a equivalence point, you needed 28.0 milliliters, and the initial pH of the acid is this, 1.75, and the pH at 14 milliliters is 3.000. Now, why do we care about the pH at 14 milliliters? Well, this is exactly half of this. So in other words, our pH half is equal to 3.000. Now, if you want, you could kind of make a small kind of rough graph of this. So if you wanted to just to help you think, you could kind of make a rough graph. Okay, so right here would be, right here is your equivalence point, and that would be 28.0 milliliters, and right here is about halfway in between there, and this would be 14 milliliters. 14.0. Right here is your pH half. This is going to be pH of 3. Okay, our initial pH is way down here, which is going to be 1.750. Okay, and yeah, so pretty much everything you need to get started. So what I want you to do is calculate the Ka with this information and this kind of graph that we made together, and calculate the initial concentration of the acid, and then I want you to calculate the concentration of the NaOH. Now, how you're going to calculate the concentration of NaOH is just using stoichiometry. So no ice tables or anything like that. You're just going to use the concentration of the initial concentration of the acid, and use stoichiometry to figure out what is the concentration of the NaOH. And you'll have to use the amounts of volume for these things in order to calculate that. And then finally, you have to tell us and say, is the solution at equivalence point an acid or a base? Okay, so take a few minutes, put the video on pause, and try to do these questions. So put the video on pause and try and finish this stuff up. Okay. Hopefully you came up with you did put the video on pause, and you came up with a few answers. So let's go over what you got. So the first thing that hopefully that you got was calculating the Ka. So Ka was pH. You use the pH at a half, which is equal to 3.000. Now, Ka is going to equal 10 to the minus 3.000, and therefore our Ka equals, now this is, remember, this is 3 sig figs. I know it looks like 4 sig figs, but since it's on the pH scale, we only count after the decimal places. So this is 3 sig figs, and this is not on the pH scale, so this is now 3 sig figs, 1.00 and times 10 to the minus 3. So here's our Ka value that we calculated. So you don't have to show how you derive the formula. You can just go Ka is equal to 10 to the minus pH half. And now we're going to calculate the initial concentration of the acid. But before we do that, we're going to calculate the concentration of H3O plus, the initial concentration of H3O plus. So how do we do that is we go H3O plus initial is equal to 10 to the minus 1.750. So in other words, our H3O plus initial is equal to 10 to the minus pH initial, and that equals 0.01778 molarity. Okay, now so these are two important pieces of information that we need in order to calculate our initial concentration of the acid. So again, I'm going to write out a small formula for the acid, which is HA, and before any OH is added, it's just put into water, and that forms again an equilibrium, and H3O plus, and we're going to change some of our letters around not to get confused, and A minus. So we're going to make again our ice table. So again, we want the concentration of our acid, and the initial concentration of H3O plus is 0, but at equilibrium our concentration of H3O plus is 0.01778, and since it's 1:1:1 ratio, this is also 0.01778. That means that this increased by 0.01778, and this increased by 0.01778. Now, that means this had to decrease by a factor of 0.01778, and therefore at equilibrium our the concentration is HA minus 0.01778. So again, our Ka is going to equal the concentration of H3O plus times by the concentration of our A minus divided by the concentration of HA at equilibrium. So HA at equilibrium is going to look like something like this. (0.01778), and since there's two of them, you can just square that, divided by, so I'm replacing our HA with this value right here, minus 0.01778, and remember this is equal to our Ka, which we calculated earlier, which is 1.00 times 10 to the minus 3. If we solve this part right here and if we solve this part right here, and we solve for HA, what we'll find is that HA, so the initial concentration, what we're solving over here, HA will equal 0.334 molarity, and this is our actual final answer. Okay, so 0.334. Okay, now moving on. I know this page is getting a little bit cramped, but now what we want to do is we want to calculate the concentration of NaOH. So now that we have the initial concentration of the acid, we're going to calculate the concentration of NaOH. So what we see here is that 0.334 molar of our unknown monoprotic acid, HA, and I'm going to change this into moles of our acid. So I'm going to times that by our liters, which is 0.0250 liters. Now, since it said a monoprotic acid, it's going to be a 1-to-1 ratio, because one hydrogen is going to react with every one OH. So a monoprotic acid is going to have a 1-to-1 ratio with NaOH. So 1 NaOH is equal to 1 of our monoprotic acids. Okay, and now our unit, after we do all of this, it's the moles of NaOH. But the question was asking, calculate the concentration of NaOH. So we want that to be moles per liter. So we have moles of NaOH, and we're going to divide by the amount of liters of NaOH that we used. And that is going to be 0.2, I believe, 0.0, we use 28 milliliters, I believe, 0.0280 liters. Okay, so 0.0280 liters, because we use 28 milliliters of NaOH, and that gives us a concentration of the NaOH, which suggests that it is 0.298. Okay, so since this reaction is at equivalence point, all of the NaOH is going to react with the HA, and so we don't have to worry about an ice table. It's all going to react at the equivalence point, and therefore we can just use stoichiometry to solve for this one, and we see that the concentration of NaOH is 0.298. Now, the last question: is the solution an equivalence point? Is the solution at equivalence point acidic or basic? Well, every time you have a weak acid, so every time you have a weak acid plus a strong base, it'll always make a basic salt. Okay, because a weak acid will make its conjugate weak base. Now, a strong base does not make a strong acid. Okay, but a weak acid will make its conjugate weak base, and since it makes all weak acids make a conjugate weak base, therefore the salt is going to be basic, and therefore at equivalence point the solution is going to be basic. That's why on your titration curve at equivalence point of a weak acid strong base, it's always above 7 at the equivalence point. Okay, and what I would like you to do is I would like you to try doing some of these problems in your book, and you can work on page 176, questions number 125 and 126, as well as some of the worksheets that you may have been given or may have gotten. Okay, so next time,